So I'm Max. I work in integral eye science, and I'm gonna present a cluster via adaptive spectral processing. This I will just showcase the application image for this one, and a little bit more about integral eye science. The integral eye science is an ad tech company that does contextual targeting and brand safety for the so pretty much we take medias and then classify them, see if it's safe, say what category it is, and use it for recommendations for advertisers. So the motivation of this is brand safety and contextual understanding. The more as we getting more and more into a higher fidelity models, the customers started wanting to more and more nuanced understanding of the scene and the content. Like they mentioned, like for instance, on the left, it mentioned like drunk driving. It does mention alcohol, does mention drinking, but it definitely don't want your beer to be showcased in this uh in this website because that will be a very negative sentiment. So what we want for the method to get that is we want universality in the sense that it cross modality, is scalable, is modular. So, and that means it can be used on any embeddings, and meaning it's embedding driven, so it can be used on any embeddings, and it's easy to implement, so it can be directly applicable, and doesn't have as little hyperparameter as possible, and and ideally is a supervised model, meaning it's future proofed. I was given this task as I joined the team, and then I come out with the thought process is this. I want universal, then clustering the way to go for global feature. The special clustering the best, but special clustering itself need manual setting of clusters, and then I come up with a CLASP, and then in the fundamentally changing the way to a degree on special clustering. By the way, a little bit background. I'm a physicist by training. You will see why soon. Um, Here's the workflow. We take an image and then using DINO to embed and take the embedding of different all the patches and then calculate the affinity matrix and then we use affinity matrix directly instead of taking Laplacian to calculate eigenvector and eigenvalue. And we use eigengap heuristic and silhouette score to calculate optimal number of clusters. Then we got a patch level using that optimal number of cluster to cluster using get a patch level segmentation, and then using the classical computer vision method like DenseCRF to get a pixel level segmentation. So the method is relatively simple. The eigengap method is essentially just using elbow method. You take the first index, where this plot x-axis is a number of index, y-axis is a value of eigengap. Eigengap is the eigenvalue of the affinity matrix lambda I minus lambda I plus one. So you just see and then connect those two dots to the beginning to the end of the index, and then just draw the distance from different data points to this line and to see which is the furthest, where here it is the furthest, and consider that as elbow. And then that elbow represent the eigengap is the biggest. The eigengap being the biggest represent there's the most significant separation from this of the different segments. And then the one after that, the segmentation significance reduced drastically. And that thus we use elbow method. If you want it, this next step is optional. If you want to even be a more precise, you can take that and just scan the band that you desire, and then calculate the silhouette score to as a measurement of separation. And then we got the optimal number of cluster and then use that to for spatial clustering. The background of the spatial clustering, that's the crux of the problem. You can draw the vanilla spatial clustering and you will find out the performance definitely not state of art. Um, and this half by accident, as most physics or scientific finding is. I instead of using calculate the Laplacian, which is traditional spatial clustering, do the diagonal matrix minus affinity matrix, where affinity matrix is just a cosine similarity because I'm using DINO. I just use affinity matrix by itself because I think that makes more sense. Like I don't see why I need to use that, maybe by instinct or maybe by luck. And I find out I somehow get a state-of-art performance of a self-supervised learning. Let me show, and then after that, I look back to it and then look back deeper into the spatial clustering and then ponder among myself and then go back to my fundamental, which is this to see actually thankfully the spatial clustering is based on physics. So basically what spatial clustering does is is analogous to a unit mass spring system potential energy to calculate the eigenvalue of that. So the left plot shows the blue is just a unit mass, just like you imagine it just like a ball with a one kilogram. And then the orange line is a spring where the where the W is pretty much the coupling between the different mass, meaning like the connection between this and this. What is what is the elasticity between the mass? So you can imagine the eigenmode of this system is like this. It's just like those three moving on the left, those three moving on the right. That's a top eigenmode. You can see that's where you want to cut. Namely, this will be a good separation. That's how the traditionally um, the spatial clustering works. However, I th this way you can imagine in your mind this is very biased towards locality. Imagine if you have a mass 1D spring system, if poke one, it will only vibrate near its locality. Thus, it doesn't have a global understanding, like global enough understanding. Coming into the ferromagnetic domain, which is pretty much a bunch of spin, bunch of you can imagine a bunch of tiny magnet misaligned as unmagnetized magnetic material. You put a magnet next to it, it will become partially aligned, and then that partially aligned and it will divide into different regimes, and that regime can be considered as a good separation. Where there's here the eigenvector is a spin alignment, and eigenmode eigenvalue is Hamiltonian Hamiltonian energy. Um, enough of physics. So in the grand scheme of things, what it does is the ferromagnetic using affinity matrix itself instead of taking Laplacian will give us a more global view. Effectively, each patch will have a global view of the entire image to a degree. The previous traditionally reason why people use Laplacian um, uh, for the for spatial clustering is partially because um, the affinity matrix is messy. But as we have a much better much better embedding algorithms is all like well regularized and normalized. Um, uh, uh, Going for Laplacian is counterproductive. So thus I just give you an overview of what why do I use affinity matrix instead of use Laplacian. So we're going from a spring system to a ferromagnetic domains. This is I'm trying to really hard to convince you because that's in my humble opinion is a relatively big leap in the sense of what we can do to the very fundamental clustering algorithm because we have much better embedding method. You can imagine in your mind the magnet have a lot of you have tiny lot of shaving of magnets and then put a magnet on it, you will see it will become regime, different patches, and it can since it's magnet, it will feel the tiny magnet feel remotely, where the spring system works really well for sparsely connected system, and it have a relatively more local feel. Anyway, enough random physics. A little bit more about the application and results. So this is what you see, just some buildings, some hedges, grass, tree, cars, road and stuff. And then we take affinity matrix, and then you can see the affinity matrix is orange here. It says 6 is the optimal, whereas the Laplacian, the elbow is a 12, which is way off, and you can see that it is more is not as smooth and yeah, and irregular. And here is what you will see on the using Laplacian for clustering. Here is using affinity matrix itself. You may see this familiar because maybe back few years ago, that's what the result looks like using classical spectral clustering. The performance, it outperform the previous state-of-art unsupervised segmentation method by about 20% on COCO-Stuff and ADE20K on both patch and pixel variant. Here is out of sample. Shout out to Shirley, which is my colleagues. This is pretty much the daily life of her pets, and then you can see those are the previous state of our method. Here's our method on the pets, and you can see a have a much better clustering and understanding of cat and dog is different, and then the pet is not part of the couch. Um, so the application is relatively vast because it is a twist on the general clustering method, and this method is used on all can be used on all embeddings, on all high quality embeddings. So it can be used for brand safety like image labeling, retrieval, segmentation, and other modality like videos and audio. So remember that the workflow, this is the part that is innovative. These are we can just plug and play on anything. So meaning we can use we can have better embedding in the future and use that instead. So meaning we can use that for podcast, and we can take the we can embed the picture, and then you can see if I want to retrieve a gun use some reference picture, then here you got that. But if you save all the patches, it will be very expensive. So we can just embed those, do a min pool of different segments, and then we can effectively create a vector database of different objects in different images or different modalities, and you can use a reference object or reference embedding to search for what you want to see. And you can see that's That's pretty much on different patch you use a reference like the gun to see it, then you have a pretty good way to distinguish to retrieve what you desire to have. The advantage of the CLASP is it have global sensitivity. It has it's general purpose. It can apply for any good embeddings, and there's zero shot, meaning it's completely unsupervised. Does not need any input ideally, unless you want to do the scanning using Silhouette. But of course, this is highly sensitive. It has a limitation. It is highly sensitive to embedding qualities. The computer scaling is n to the three n cube for the eigenvalue calculation, but there are some heuristics that can be brought it to n log n if you want to. In the future, we would like to extend the clustering algorithm to other modality, and we'll optimize the compute scaling to using some approximate decomposition, eigen decomposition method. And this work is impossible without the help of the support and my great colleagues in the integral eye science, and thank their insightful feedback, and also special thanks to Shirley's allowing us to photograph the PT, Stevie, Minnie, and Annie, who was a model in the out of sample demonstration picture.